Yes.
Okay, great. Okay, as I said, we have a lot of things to go over. It will increase a little bit in complexity as we go along the way, but we'll start with something simple. Who am I? And what's this weird name that nobody seems to be able to pronounce? Then we'll talk about the James Webb Space Telescope, JWST for short. We'll look at what astrochemistry is, then what these mythical polycyclic aromatic hydrocarbons are, or PAHs for short. And we need to do a little bit of a spectroscopic primer because a lot of the details that's behind these beautiful images is hidden in the spectroscopy. Then we're going to look at PAHs in space. Then we're going to apply a more detailed view to the PAH spectroscopy itself. Then finally, we're going to get to something that's really dear to my heart. That's the NASA Ames PAH Infrared Spectroscopic Database, PAH-DB for short. As you see, there's a lot of acronyms already going on. And then we'll end with mining the treasure trove, and that's where we apply all this knowledge that we have gathered to try and understand the astronomy, the astrophysics that is going on. I'm going to click. So, who am I? So as you might have gathered from my funny name, 2 A's in the name, and last name Boersma, and perhaps even a little bit my accent. I'm not natively from America, the US. I'm from a small country in Europe called the Netherlands. There I'm from a very small village called Gietjerk in the northern of the country that borders the North Sea. And we're living in the province of Friesland, and Friesland is quite unique, like where the rest of the Netherlands typically speaks Dutch. We have our own language, and that can all the way be traced back to the old Viking days. A lot of proud history over there. You see here on the screen the Dutch flag, the red, white, and blue stripes, and then below that is the Frisian flag. These are not hearts; these are lily leaves. So I went for my studies to the University of Groningen, the Captain Astronomical Institute, which is not too far, especially considering distances here in the US from where I grew up. As part of my PhD, though, I traveled quite a few times to Moffett Field here, to NASA Ames Research Center, because it has a really solid astrochemistry group there. When I got my PhD, I was lucky enough to get a NASA postdoctoral program position. So I did that for 3 years. And then I moved to the San Jose State University Research Foundation, home out full again. And that's the position I currently hold. And I'm still working at NASA. I've been very fortunate thus far to have been able to observe with some of the world's foremost telescopes. Here are a few ground-based ones and Sophia. These are pictures I took. So it's my own little private collection. We have the VLT, the Very Large Telescope here in Chile. That's gorgeous there. This is one of the smaller telescopes. The 8-meter ones are behind me. The Orion Radio Telescope in Spain. And here I'm sitting at the James Clerk Maxwell Telescope in Hawaii. That was 2005, when I was quite a bit younger, but I'm actually doing some observations there. And just for fun, I put Sophia, which is the Stratospheric Observatory for Far Infrared Astronomy, another acronym, which was flown here from Ames, but well, not flown from Ames, but managed from Ames, but unfortunately that project got cancelled. Okay, so the James Webb Space Telescope, JWST for short. JWST was launched Christmas morning, 2021. I guess depends a bit on your time zone, but for the morning you see some footage here of the launch. Here, this picture that is me and my family getting up in the wee hours, not for Santa, but for to watch the launch. As you can see on the bottom right for you guys, that's the telescope unfolding. That was one of the tricky parts that everybody was very nervous about. It that went all okay. I would like to recommend a Netflix episode of Unknown, which actually talks about the lead up to JWST launch and everything. I think it's an hour or something, so you can look at that. That's really, really nice. There's also a 45-minute YouTube video, which you can access with a QR code, because that's how we do things in modern days. And that's a 45-minute YouTube video by Fraser Kane, who talks about all the results from the first year of JWST. That's all very, very interesting. So what is the James Webb Telescope? Well, it consists of 4 instruments, NIRCam, which is an imager, that's the cam part, NIRSpec, that's the spectrograph, that's the spec part, and then MIRI, which is both a spectrograph and an imager, and the same for NIRIS. These instruments can be used in all kinds of different configurations, if you will, like coronagraph, integral field units, and interferometry, sorry, words. So one with the challenges was, of course, unfolding of the telescope, but what then needed to happen was aligning all the different mirror segments, and that's what you kind of see here happening in the different images that are popping up. However, the most spectacular image, I think, is this one. This is the telescope alignment evaluation image, and you see indeed a beautiful star at the center of the image and these nice reflection spikes, but that's not what the amazing thing is. All these little fluffy, flossy, nebulous things, those are galaxies. Every single one of those is a galaxy. Even in the alignment image, they were already popping up. It's just spectacular. I'm sure many of you will have seen some of these images when they came out. I think it was a big event with the president and a bit awkward in my opinion, but I'm sure you all saw it. So I reproduced here the images showed of the Carina Nebula and then also the Southern Ring Nebula. And for the Southern Ring, there are 2 different wavelengths, well, 6 different wavelengths, but 2 different instruments. And the most interesting part here on the far right is that JWST resolution is so amazing that it was able to separate out the 2 stars at the center that make up the binary star system. 2 over there, that's just amazing. A program I'm personally involved with has looked at the Orion Bar. The Orion Bar is in Orion, and you can kind of guess why it's called the Orion Bar, because there's this bar-like structure going on. And again, this is a spectacular image. But as we saw, JWST doesn't only do spectacular imagery, it also does spectroscopy. So, and we'll go into that a little bit more later, but you see here a spectrum from the Orion Bar. So we were, of course, very proud of our Orion Bar observations, but we weren't the only ones, because former President Barack Obama highlighted our project and our observations on his Instagram profile. This is a screenshot when he did so. So we thought it was pretty neat. So, okay, now we need to define some terminology, astrochemistry. So Wikipedia, maybe not the most trustworthy one, but you know, we can work with that. So what is astrochemistry? Astrochemistry is the study of the abundance and reactions of molecules in the universe and their interaction with radiation. So there's a lot of going on already. The discipline is an overlap of astronomy and chemistry. And it can be applied to solar system, interstellar medium, and you know, all the rest. So, but it's the study of molecules and chemistry and reactions and interaction with light. So when studying astrochemistry, a very important aspect here down on Earth is laboratory astrophysics. So what that entails is that trying in the laboratory to simulate astrophysical, astronomical, astrochemical conditions and then see what happens, right? And just to kind of give an example what is done at NASA Ames, this is a picture in the back, the big picture in the background of the Institute for Carbon Evolution experiment at NASA Ames, and that is just there to show you kind of the type of engineering and the complexity that is involved in doing this type of work to try to understand the astrochemistry. You do laboratory astrophysics. That's basically it. The image at the bottom right is an artistic impression. That's not really a real galaxy in there, but it's kind of trying to give the impression that doing this experiment, you get a window onto how galaxies form and you know the chemistry, because it's called a window, that round thing. So yeah. Then polycyclic aromatic hydrocarbons, PAHs for short, another term to define. and Wikipedia here again to help. So a polycyclic aromatic hydrocarbon, PAH, is a class of organic compounds that is composed of multiple aromatic rings. You don't need to read that. I would bring your attention to the last line here, is that as polycyclic aromatic hydrocarbons are discussed as possible starting materials for abiotic synthesis of materials required by the earliest form of life. So these type of molecules might be important in astrochemical sense and astrobiological sense for the formation and evolution of life on early Earth, or maybe, somewhere else. So kind of to break it down a little bit more. So multiple rings. Well, we have one ring here. That's called benzene, very well-known compound. But then we just add rings to it. And then here we now made the PAH coronine, very PAH favored by many. And then, dissecting the naming, we already saw it a little bit, but polycyclic, poly, many rings. Aromatic, it has kind of two aspects to it. One aspect is that chemically that often refers to very stable compounds, they're very sturdy, but also in carbonaceous materials which have aromatic units in them, they're often very smelly. So aroma comes from aromatic. And then hydrocarbons, so they're made up of hydrogen and carbon. So what I'm showing here in green is the carbon lattice, and then at the edge of each ring would then a hydrogen be sticking off. You can see that a little bit better in this creative swirl of PHs, which tries to bring across that, well, you can arrange these rings in many different shapes and forms and different sizes. You have 2 rings, 5 rings, 100 rings, right? You can, in all kind of different shapes. Besides that, you can also cheat a little bit maybe and add in other compounds like oxygen, magnesium, silicon, iron, or nitrogen. So that's some of the different colors you see there. So yeah, it's a class of molecules, and you can, think of every shape you want. But now you've seen this shape, you're going to see it everywhere because it's a very famous shape. First, of course, chicken wire. Sometimes we introduce them as these are chicken wire shaped molecules. But you can also see them as a window at a Topaki Palace in Istanbul. Not to forget, the primary mirror of JWST has the shape of a PAH. It's very appropriate, I think. And then, you can also see the shape in cartoons like here, Miles from Tomorrowland, where they use it as, I guess it's a kind of shield thing. Going into Miles of Tomorrowland a little bit on a side note, me and my family had the opportunity to be at a series premiere, which was held at Ames, and we met the director, you see him on the screen, of the Miles of Tomorrowland series, and also the real life that was advising. So why is it? The screen does not show the same. Screen does not show the same. Oh, now it does. Yeah, with that. Glitch in the matrix. So, as the Wikipedia article is, on Earth we can find these type of materials in crude oil, coal, combustion products like car exhaust, and when you cook, fry things, etc. If you're able to isolate the compounds, so you have a bunch of only that PAH, they can actually be pretty colorful. Invisible light you can see on the top, and then they have a particular characteristics that they often fluoresce as well. So if you put UV light on it, they'll start glowing brilliantly. Yeah, as you can see in the image here. So now we need to do a little bit of a quick spectroscopy primer, just to get a little bit of a footing in here. Maybe you already know this, but we'll try to go quickly through this. So when there is sunshine and rain, you have the opportunity to see a rainbow. And what happens there is that the water dissects the light into its different components, into its different colors, if you will. You don't need water for that. You can also use a prism. So that's that triangle thing over there. So you put a ray of light in, and then that spreads out. Well, you know, at school you learn the different colors in a song, but scientists use numbers. So instead of talking in colors, we often talk in wavelengths as the unit. So we talk about wavelengths. Then instead of only, or besides looking at the specific color, which we now call wavelength, you can also look at how bright or how intense the emission is, or the color is. So, and then if you plot those against each other, so on the x-axis, if you will, on the horizontal axis, you do the wavelength or color, and then on the vertical axis, you do how bright, then you have a spectrum. So now everybody knows what a spectrum is. What you see here is the spectrum of the sun, and it has been extended beyond what we can see with our eyes, beyond the visible. Spectroscopy is a very important tool in general science, but specifically in astronomy, because, you know, the only thing we're getting from the cosmos is light. You know, I guess some particles maybe, but mostly light. So here again, a beautiful Wikipedia picture. So how can we use spectroscopy now to figure out why this firework is orange? What is causing this firework to be orange? Well, what do? We put a light through a prism, and then we get our bands like we saw before. It splits out the colors, and then we do the scientific thing, turn it into a spectrum, and now we have the signature of this fireworks. And as you can see, there's a bright peak around 580 nanometers here, which is orange. But you know, but there's also some little bumps around it. So then what one would do is one would go to the laboratory, and you would have samples, collections of different materials, what you know they are, and then you just burn them, because that's what fireworks does, right? It just burns it. So, and then that light you collect through a prism and make a spectrum, and then is simply trying to match up what you saw out there on the beautiful blue sky and the firework. I guess it needs to be night. And then you compare which of your compounds matches best. And what you'll then find is that actually sodium, that is part of just regular kitchen salt, matches best. And you know, and you probably all know this, right? The colors of fireworks are made by adding all kind of different materials to it. And here's just an overview of that. So yeah, now we've got a good foundation of everything. So now we're finally going to pass in space. So starting off hardcore, this is a spectrum. This is the spectrum of the Jewel Bug Nebula, also known as NGC 7027. And this spectrum has observation, but also a prediction in it. So the prediction that people thought the spectrum should look like is the dashed line, the red dashed line. However, this turns out not to be the case when the observations were made. There was this mysterious excess emission. And then, of course, you know, kind of do a similar approach as with the fireworks. You go to the lab and you try different compounds and see if you can reproduce this type of signature. This was only possible through the Kuiper Airborne Observatory, which was flown from NASA Ames, which was able to take, instead of those few points we saw earlier, to get a proper spectrum. And that's the one you see here on the right. Laboratory experiments on PHs, as you might expect, compared very favorable to the observations. And you can kind of see, you know, a bump here, there's a bump there, etc., etc. So the general structure seems to match. So this was the start of the hypothesis. So the idea that it could be passed, and you know, as good scientists, what you do, you apply the scientific method, and that means make and test predictions. what we would also do is gauge the astrophysical considerations for the PAH hypothesis. So what does it make astrophysical sense? And then, every astronomer's dream is to just get more observations. You always want more observations. So, lab prediction 1. In the lab, it was seen that there's emission, or absorption in this case, but that there is a feature between, or features between, 13 and 50 micron. However, from Earth you cannot observe that, because that's where the CO2 in the atmosphere has a strong absorption. However, around that time, IRIS was already up, which is the Infrared Astronomical Satellite, which was lost in 1983, and people went back into the archive and were able to stack a lot of spectra together, here 20 sources it says, and indeed they found a little bump that's indicated with the arrow that lined up with the PAH emission. Another prediction is shown here, where the lab spectra showed consistently 2 relatively weak features. They are highlighted here by the dotted lines, between 5 and 6 microns, more specifically around 5.2 and 5.7 micron. And again, the Kuiper Airborne Observatory to the rescue, observing BD 303639, it found these 2 bumps in the observations. So then we need to kind of think about the astrophysical considerations. What are the how does everything connect astrophysically or astronomically, if you will? So the first thing, it's a little bit tactical, but I think generally it should be okay, is that these features were observed in objects where it would not be possible for the carrier to be excited thermally or through collisions, if you will. So this would then imply that the actual carriers were free gas phase molecules. The second observation was that the intensity of the band, so how much you would see, was directly correlated to the carbon abundance that were independently measured. And then third, these features were observed in extremely harsh environments where simple molecules would not exist. And together with the predictions and the confirmations we saw before, all of this points to PAHs. So at this point, we went from PAH hypothesis to a PAH model. So we evolved in the scientific process. And this in 1987 was one of the first kind of acknowledgements of that, stating that the identification of PAHs in astronomical infrared spectra is firmly established. So that was a big point. But at that point, there weren't that many spectra of PAHs yet, which would be needed to further refine the PAH model and use it as a new probe of what's going on in the cosmos. And to address that astronomical problem, here at NASA Ames Research Center, a program in 1990 was established to build a PAH infrared spectroscopic database. Foreshadowing. So the early laboratory work for about at least a decade, it was able to keep up and hold up the PAH model, if you will, and things evolve. As you can see here, there's a stick spectrum comparison and then more advanced comparison to the right. But as we saw earlier, PAHs can exist in many shapes, forms, sizes, etc. And in the lab, it can be very difficult to measure those spectra because, you could have it could be a very expensive compound. Can you even make the compound? Some of these compounds are toxic. A whole slew of problems that could happen there. But fortunately, in the 1990s, quantum chemists were able to show that they could compute with high accuracy. So this is computing on a computer very accurately the spectrum of a PAH, and you can see a little comparison here, and all the sticks match up pretty good. So this was a major breakthrough because it was now possible to use to compute all these different shapes and forms and compositions and see how they fit in with the astrophysical question here. So then there's of course also the astronomers who need to be kept happy. So we entered PAHs in the space age with foundational work from the IRAS telescope, but what really put PAHs on the ground, if you will, is the Infrared Space Observatory, or ISO, which was the first observatory that could take a spectrum, an infrared spectrum across a huge wavelength range. And these two spectra you see here, the red color, that's all PAH emission. And what ISO showed was that these PAH spectra vary spatially across a given object, but also from object to object. And this then implies that these variations reflect changes in the underlying PAH population, so sizes, charges, things like that. And again, this is connected to changes in the astrophysical environment. Then Spitzer came along, launched in 2003, and Spitzer had a significant increase in sensitivity compared to ISO, and it was able to show that PAHs are everywhere, and there are lots of them. And here are some beautiful examples. All the red you see in these images is coming from PAHs in our own galaxy, in other galaxies, in the spiral arms you see there, but even outside galaxies, where it's being blown out by supernova and all kind of exotic processes. And slowly but surely, a picture emerged from how PAHs formed and evolved. So the premise is then that PAHs are formed in the outflows of carbon-rich HEB stars or in shocks generated by supernova explosions. They get pushed into the diffuse ISM. Then over time, they get coagulated again. They form dense clouds. The next generation of star and planets formation happens. A solar system forms, and potentially they rain down and, you know, are important for these first aspects of early life. And then once this solar system evolves further, it can become an HEB star again or explode as a supernova, and we have a nice cycle. We like cycles. A life cycle of stars and PAHs. So it was then well established that PAHs are very significant. And I'm just going to read these out, but these are important points. Up to 30% of the infrared emission is carried by PAHs. So it's not only a lot of things, a lot of different objects, but it's also a lot in these objects. So 10 to 30% of the cosmic carbon is locked up in PAHs. So that's an accessible source of carbon. PAHs play an important role in energetics and chemical processes in the interstellar medium. They are the largest carbonaceous and most complex molecules known in space. PAHs are more abundant than all other known interstellar polyatomic molecules combined. PAHs are found in meteorites, extraterrestrial interplanetary dust particles. PAHs represent the single largest source of biochemically accessible carbon available in our own solar system. We looked at that a little bit before. And PAH features can even trace back to the first appearance of carbon in galaxies on cosmological timescales. So, you know, I think JWST found something at Cetus, what is it, 3 or something, right? Only a couple 100 million years after the Big Bang. The interest in PAH research has seen a quick evolution. This is from 1980 up to now, and you can kind of see a steady ongoing trend, and then there's suddenly a jump where it significantly increased the number of PAH papers that were produced per year. And if you look carefully, that's around 2003. That's when Spitzer launched. So we're kind of expecting another jump now that JWST is flying. Although it makes it very difficult to keep up with all the literature. So many papers. Speaking of JWST, now we're of course in the JWST area, and we already and we already saw that the PAH emission is everywhere. The PAH emission is everywhere, and there's abundance. So that only means that JWST will see PAH emission, if not in all, at least in most observations it will take. And then it can either be a useful thing that people are interested in these type of emission features, or they want to get rid of them, but they're there. So just to, once again, to emphasize JWST's stunning capabilities, and taking as an example the Orion Bar here. On the left, you see a Hubble color image, which is, Hubble does a good job, looks good. But then you look at the JWST, it's at least on par, if, I'm a bit biased, arguably better. Arguably better. But when we talk about these PAHs, we can actually look at images in the PAH band. So these are two images that look at the PAH emission at around 3.3 micron. We'll talk about that in a little bit. And this is on the left is a Spitzer image, and JWST is on the right, and it's clear, right? It's blown out of the water. It's blown out of the water. It's just amazing. Okay, so now we're gonna take a little bit of a deeper dive into the PAH spectrum, and we'll start by looking at the isospectrum of the Jewel-Bot Nebula. We looked at that before, and what astronomers like to do canonically is draw some kind of baseline continuum. Here that's shown as the dashed gray line, and then we zoom in and we see a beautiful PAH signature. We see a band at 3.3 and between 5 and 6 micron. Those were those two bands that were so important for turning the hypothesis into a model. And then there's a whole bunch of other bands, and then at the end there's the two bands that were also so important for the going from hypothesis to model. And interestingly, each of these distinct features is associated with a specific vibrational motion of a PAH molecule. Here's our friend coronine, which we built earlier, and it shows that the 3.3 micron is due to CH stretches. So the C is the carbon, the H is the hydrogen, and you see it stretching. The 6.2 is due to carbon-carbon stretches, and the 8.6 due to CH in-plane motions, and then the 10 to 50 micron region due to CH out-of-plane motions. I should make clear that the actual motions are highly exaggerated, just for demonstration purposes. Molecules not doing this wild. So, and this is predominantly from ISO. When they gathered a lot of spectra from different objects and had a big sample, they were able to characterize these spectra into 3 classes, A, B, and C. And this is just a simplified cartoonish illustration, but you can see, there are some difference in shape of the different bands, and the peak positions shift a little bit. But more interestingly is that this class assignment correlates with the type of object you're looking at. But now we can flip this around. So if we take an observation of an unknown object in the sky, and we determine the class it is, we know the object type, right? So we turn this around. And this is just one example of how the PAH emission can be used as a probe tracer indicator of, whatever you want to call it. And it's a long list, and don't worry, we're not going through all of them. We'll look at charge state, and we'll look into some chemistry. So starting with the charge state. So here now we're looking at a spectrum taken with the Spitzer Space Telescope of the Iris Nebula. And again, we'll start off by drawing, a broad type of continuum. But instead of now looking at the overall shapes and where the peaks fall, we just measure how much is in each of these colors. So how big is it? If you look at laboratory spectra, here a mixture of neutral PAHs is compared to that of a mixture of ionized PAHs. There's a striking thing happening. and that is the emission between 6 and 9 micron for these ionized PAHs is relatively way stronger than that around it. Vice versa, for the neutral mixture, it's the bands outside the 6.6 to 9 micron region that are relatively stronger. So now we have a tool to determine what the ionization is. So what fraction of the astronomical PAHs are neutral and how much are ionized. And we can do this by just taking a band that is part of the blue area, like the 6.2, and one that's in the red area, the 11.2. So here we have a tracer for PAH charge. Chemistry. We have two chemistries. This is the first one. So we had this classification going on where the peak position of certain bands would shift. Here we're focusing in on the 6.2 micron band. And if we go from class C to B to A, we see a shift to shorter wavelengths. One explanation for this could be that in the PAH itself, we're introducing nitrogen. So each of these different colored balls that replace a carbon atom is a substitution with nitrogen. And then on the left, you see that what happens to the spectrum. And basically, it shifts to shorter wavelengths. Another example of chemistry is deuteration. So we saw these CH in-plane modes, right, that were at 3.3. But then what can happen is that these hydrogens are being replaced or substituted by deuterium, which is a heavier isotope of hydrogen. What then happens to the spectrum is that the band doesn't fall anymore at 3.3, but it shifts between 4 and 5 micron, which is shown here on the bottom. I don't know, you can see my mouse, right? Yeah, there you go. You can see that here on the bottom. People looked for this signature in astronomical observation, namely observation of the Orion Bar and M17, using ISO data. These ISO data are some of the best data that are available, and the authors of this paper argued there was a tentative detection. I don't know, but yeah, you know. But what could we do? JWST. So we have, I'm PI of this program, of a General Observer Cycle 1 program, and the title is very floral, near-spec eye view, deuterated PAHs, PAH-nitriles, and PAH-Overtone combination bands. It's just a small program, but one of the things it focuses on is trying to find a better solution or trying to find these deuterated PAHs. The program looks at 7 targets, which are shown here as observed by different observatories overlaying all these rectangles. Those are apertures from existing observations, and the JWST observations we wanted to do are indicated with the green circles. So let's kind of zoom in on one. So this is M17, where we initially considered 4 positions, so the 4 green positions. But then eventually those that were observed are indicated by the white arrow. On the right hand, you see a color composite map where the red, green, and blue channel are represented by the intensity in 3 different PAH bands. So at one at 11.2, one at 7.6, and one at 6.2. And as you can see, there are changes happening across that area that we probed. So that's why we were looking at these positions. So looking at the spectrum then that we extracted from the position closest to the irradiating star in M17, we get this extremely rich spectrum. This is just amazing. It shows our 3.3 micron PAH feature over here. Our 3.3 micron PAH feature. It shows the onset of the feature we saw at 5.2 micron. It has even some CO2 ice absorption going on, and there is a plethora of lines in this spectrum. And then you see these nice comb-like structures. Those are hydrogen recombination lines. And just to make the comparison, here in the bottom right, you see again the image we had earlier on the screen with the ISO data. The bigger spectrum on the back, that wavelength range is indicated by this little red area. So all the observations themselves are shown in like the black axis, and then all the big peaks you see, those are emission lines. And then we've constructed a model fitting everything at the same time, where we take also a component that could be due to these deuterated PAHs. So that is shown in purple. So yeah, it's again, JWST is awesome, and there's definitely there's a less tentative detection here, although it's still a little bit of magic with this extra component. But NASA Ames Bar is the Spectroscopic database bar, and that's what we're going to talk about. So what we did before was looking at things kind of phenomenologically. So what would be of greater value to us would be kind of being able to start from the ground up, so that we build up a spectrum that is very comparable to the astronomical observations instead of the other way around, where we go from the top down and go through the spikes. So what would we need for that? The next slide, that's what we need. Okay. One big question is, how do we get all these different shapes and forms, the diversity of them up? Well, we've already answered this question, of course, earlier on. The way forward is to extrapolate from laboratory measurements and then use computer fast spectra to create a spectral library. And then the magic equation is we take the spectral library, we use astronomical model and simulations, and try to use the astronomical observed spectrum. So there are a number of databases available already around the world. There's one in a French-Italian one. The NIST has a few PAH spectra, but of course, the biggest one, the best one, is the NASA Ames PAH Infrared Spectroscopic database, PAH-B. It has the most. It has over 10,000 PAH spectra in its next release. On top of that, it's not only the spectral data that it offers, it's also a website. And the website, of course, these days to be modern, but you can actually peruse the data there, the content of the database, and you can download the data, and there's some simple rudimentary tools where you can do some exercises with the data, and there's suites of software tools that astronomers can use to do the actual data analysis. You see here a map of the world with every red dot showing where people visited our website. So we try to filter out all the spam and all that kind of stuff. So this is relatively legit, I think. PAH-B has been applied to many astrophysical and astronomical problems, ranging from things related to our own solar system, like Titan, and again, to entire galaxies. So getting back to what we want to achieve is that we want to reproduce the richness of the astronomical infrared spectrum from the ground up, and through this gain an understanding of the astrophysical and astronomical history and environment. So again, what do we need for that? Well, we need a PAH spectral library. Check, we have that. That's PAH-B. How are we going to try and compare the observations with the spectrum we create? We use a fitting algorithm for that. We basically just do a fit, and then we need a PAH emission model. And we need a PAH emission model because the data in the database are in absorption, and the spectrum we observe from the sky are in emission. So what this emission model needs to encompass is that it needs to get from the environment certain photon energy, and then the molecular physics will tell it how it absorbs that photon and then re-emits that as infrared photon. So fortunately, all these things we've included in the PAH-B software tools. So this is a little timeline of how models, lab, and theory all go, and astronomical observation as well, evolve kind of hand in hand. way in the beginning we saw this. Early on, the observations were just simply compared to stick diagrams. So these stick diagrams are measurements in the lab, and they have a general coherence between the two. And a little bit later, improvements of the astronomical modeling part, we're actually able to create spectra, and that looks very nice as well. But then later on, of course, ISO came along, which had a much broader wavelength range and also higher resolution, and still the laboratory data matched relatively well. Then in 2010, PAH-B was launched, and not long after, it was used to apply the little the ingredients, I guess, the recipe we had to analyze these things. And here it analyzes the three different classes we saw before, A, B, and C, and it does a very good job. Then with Spitzer coming around, PAH-B was used readily all around, and this is an example of a spectrum of the Iris Nebula, where we did the spectrum, and then we broken them down into contributions from different charge states. So that's the PAH cations, neutrals, and anions. So those are the different colors. But then, of course, we are today. Yesterday, as the slide said, today we have JWST, and here again is our friend Orion Bar, and this is a spectrum of the Orion Bar where we fit it with PAH-B. The animation already finished. Oh no, it's still going. Still going. Yeah, it takes a little while. So the red is the actual fit. It tries to fit the black points. As we said many times now, there's also a continuum type component underneath. It's shown in orange, and all the gray points are being ignored because those are emission lines and other things that are not PAHs. So now we've got all this tools and all this knowledge, so we can apply this to some astrophysics. So we call that mining the treasure trove, all the hidden information that is in these data. So taking an example here, this is the Iris Nebula and NP7123, which we talked some spectra about already. If we then zoom in at its core, or center, where there is a Hubble Space Telescope image available, and then we can kind of box in the area on that where there's Spitzer data available. So you see the little pixel. So there's about 300 of those pixels making up that box, and there's a spectrum at each position. And what makes the Iris Nebula such a good target is that you can clearly see there's a demarcation between a much more diffuse region in the bottom left area compared to the top right, where there's a much denser region. And the spectra reflect it as well. So here are two spectra from each region, and you can already see, for instance, if you look at the 6.2 micron band and the 11.2 micron band, the relative intensities in both images, there is a difference. And if you remember, that tells something about the charge state of the PAHs. So when we compute this ratio, measure this ratio for each of those 300 spectra, we get a map as shown on the left here. And like the image in the right, the Hubble image, there's this clear demarcation between the dense medium and the diffuse medium. So the morphology matches up very nicely. But of course, we can go one step further when we do this PAH-B analysis that we have, where we take the library and actually the model, and then we fit the data to the observations. And then we can get back from that, like we saw earlier, the breakdown into the different charge components. And that's what's done here. This shows the fraction of PAHs that is ionized, positively ionized. And again, you can see that it really nicely matches the morphology of the 6/2/11/2 band we saw. The next natural step then is to, well, why not graph these against each other? And that's what's done here. So on the x-axis is the ionization fraction, and on the y-axis is a little bit in a different form, but a 6-2/11-2. And each point is color-coded according to different zones. You can see on the right, which were identified through machine learning. So all the height these days, so we do machine learning too. And you can see we get a nice linear correlation, a nice line, and straight things in physics is always a good thing. Always a good thing. More importantly, astrophysically, it also makes sense is that the position of a star is indicated in the bottom left corner, and that's closer to the irradiating source. So you would expect the ionization fraction, more ionization happening closer to the star, and indeed the red and the green points have both a higher ionized fraction as well. That's its ratio. However, we as astronomers don't always think in ionization fraction, but a parameter called the ionization parameter, or gamma, which connects the ionization state of the path directly to some parameter that's like the astrophysical environment. You know, it's in the bottom there, doesn't really matter. And again, it's a very nice straight line. So this was Spitzer. JWST, of course. So here again, we see the beautiful image of the Orion Bar. And the light rectangle here is the area for which spectra are available. So only that little area spectra are available, but there are 8,000 spectra in that. 8,000. So when we do that analysis, the PAH-B analysis, when we measure 6-2/11-2 and all those things, from the PAH-B analysis, we can get a map of the charge, we get the Iris Nebula, and we get also one for size. Those are the two that are labeled, and morphologically, they compare very well again to the cross cuts from the composite image here. So this can all then be tied back to the astrophysical conditions. But then we plot these things against each other, and again, straight lines, more or less straight lines. We plot straight lines, but now interestingly, and I don't know if that's kind of by happenstance or luck, but you can see that the color coding kind of nicely follows these different distances from the bar. So you have several straight lines, but their exact shape and slope depends on how far you are from the bar. And that indicates that there's something going on there that we need to, take into account. Again, tells us something about the astrophysical environment going on there. So this is hasn't even been published yet, so embargo. Well, okay, so wrapping up now. So we started in the late 1960s, 55 years ago, more than 55 years ago, this mysterious excess emission was discovered. And now, the JWST, we're using that imaging to try and understand the formation of stars, planets, and possibly even life itself. So I think that's pretty amazing. And then lastly, you might have already seen them, I brought some PAH-B related goodies, that's not merch, swag, I think is the word. Please get it while you can. I'm not sure I got enough for everybody, so there's some